Hello, everyone. I hope you had a relaxing and enjoyable spring break, and I hope that you're all well. This set of video notes is going to cover sections 4.7 to 4.14. If you recall, last time we left off talking about Newman projections, and we're going to use Newman projections to understand different energies of molecules based on their different rotational states. So the first idea that we want to talk about is the dihedral or torsional angle. This is simply the angle between the hydrogen atoms on the adjacent bond. So this is your dihedral angle right here. This angle affects the stabilities of the molecule and the rotational state because these have areas of high electron density where we have bonded atoms. So for example, the hydrogen atom has a region of electron density, not only on the atom, but in the bond. And if you look, the next closest angle, or next closest atom, which has a dihedral angle of 60 degrees, okay, there are going to be some electron interactions between the bonded atoms as well as with the bonds. So this is what we call a staggered conformation here. It's your lowest energy conformer or rotational state. But if you consider an eclipsed conformation, we have electron density that's going to repel. So this is higher energy because of the electron repulsions in the atoms and the bonds. So the greatest dihedral angle that we can achieve in a staggered conformation is going to be 60 degrees between two bonded atoms. And this eclipsing interaction, although it's drawn, they're sort of offset a little bit. There, you have to think of it as being right in front, one right in front and one right behind. Let's take a look at a potential energy diagram for ethane. Remember, we're talking about ethane. As we rotate through the molecule 360 degrees about the carbon-carbon bond, so that's here's your ethane molecule. As we rotate that bond right there, we're going to look at the different conformational states. So this might be helpful to pause the video and make a molecule of ethane with your model kit, and you could go through this rotation and see the different staggered and eclipsed conformations. So as you rotate through, you see that your staggered is your lowest energy conformation. And then when you rotate 60 degrees, you get to an eclipse conformation. Rotate it in the same direction again, another 60 degrees, get back to a staggered, and then eclipsed. And you keep rotating until you get through 160 degrees, and then you've seen all of the possible staggered and eclipsing interactions. So we say that similar conformations are degenerate. What degenerate means is they have the same energy. So let's look at all the staggareds. We notice that all of the staggered conformations have the same energy. So remember, your y-axis here is potential energy. They all have the same energy. All of our eclipsing interactions, we say that they are degenerate because they have the same energy. So the next thing I'd like you to look at is the energy difference between the two. We want to understand what's causing this energy difference. And we can explain that 12 kilojoule per mole energy difference in terms of torsional strain. And that's simply the difference in energy between the staggered and eclipsed conformations. So the reason is because of those electron repulsions. Now, in a staggered conformation, there are no repulsions. We say that everything in a staggered conformation has no energy cost. That's why it's the lowest. But the eclipsing interactions, each one of these hydrogen-hydrogen eclipsing interactions costs 4 kilojoules per mole of energy. So the total cost is 12 kilojoules per mole for an eclipsed interaction for ethane. Now this is going to change when we start adding different groups on our hydrocarbon. But for now, let's just try to understand the basics of this energy difference. It's due to torsional strain. Now we're going to look at propane. C3H8. So propane we can look at it like this. We have our CH3, we have our hydrogen, hydrogen. Let's call this a CH3, call this a CH3. Right. And let me draw it a little bit differently so you can see how it's set up here. We'll say that that's our hydrogen, hydrogen, hydrogen. So what we're going to do is look at this down the indicated bond axis, and we can get a Newman projection. All right, so what we're going to do is, using this Newman projection for propane, we can rotate through 360 degrees. Now we're going to start here with our staggered conformation. If you rotate at 60 degrees, you get your first eclipsed interaction. Rotate that front carbon. Now, if you notice, we're holding the back carbon in place. And it doesn't matter which one you rotate when you're thinking about this. It really will give you the same answer each time. We keep rotating, and we go staggered, eclipsed, staggered, eclipsed, and finally staggered once we get back to our original starting point with a 360-degree rotation. So if you remember the last potential energy diagram and set of Newman projections for ethane, we saw that the hydrogen-hydrogen eclipsing interaction was worth 4 kilojoules per mole. We have two of them here. Notice all of the eclipsing interactions have the same sort of groups. Now, remember the staggered conformation, there's no energy cost there. They're all the same. So our eclipsing interaction, we have a different group, that hydrogen-methyl interaction. Now I'm going to give you a table, or I'll always give you these values. You'll never have to memorize these. But I'm just showing you that if you look at the total energy difference, that's 14 kilojoules, and you subtract the two that we already know, then that hydrogen-methyl interaction must be worth 6 kilojoules per mole. So again, I'll give you all of these values. You never have to memorize these. So the energy cost of a hydrogen-methyl eclipsing interaction is greater than the cost of a hydrogen-hydrogen eclipsing interaction. And you notice the total energy difference is greater because we have those larger groups eclipsing each other, which costs more energy. Let's look at butane, a little bit more complicated. This is going to have some conformations that are not degenerate or not equal. So if we look at, let me just draw butane for you. Here's butane. And show you what bond we're looking down. Imagine looking down this bond axis to get our first Newman projection here. All right. So our first Newman projection is a staggered conformation, but if you notice, we have a really low energy staggered, and then we have a higher energy staggered. So we have different staggered conformations. So let's try to understand what's causing that difference. These staggered conformations that are not degenerate, meaning they are not the same energy, one is here, one is here, is due to what we call an anti-configuration versus a Gauss configuration. The anti-configuration is the lowest energy because it gets those large methyl groups as far away from each other as possible without any electron-electron repulsions. However, let's look at the next higher staggered conformation, which we call the Gauss. You notice we have those two methyl groups. Even though it's staggered, they're large enough to have a little bit of electron repulsions in the bonds and in the atoms that raise the energy by 3.8 kilojoules per mole. Again, you'll never have to memorize this. You just need to know that a Gauss configuration, a Gauss staggered, costs more energy than an anti-staggered. And as we rotate through, we can see that we end up with two different Gauss configurations, and we have two staggered configurations. So our eclipsed conformation, again, like we stated before, is the least stable. The cost of a hydrogen-hydrogen eclipsing interaction, if you remember, was 4. And the total cost for the eclipsing interactions was, for the highest eclipsing interaction, was 19 kilojoules per mole. So that methyl-methyl eclipsing interaction is worth 11 versus the 6 kilojoules per mole for a methyl hydrogen. So the HCH3 eclipsing interaction was worth 6, but a methyl-methyl is worth 11. So the larger the group eclipsing each other, the more energy it's going to cost to rotate past that. So let's look at a typical problem that you might be asked to solve. I know there's something very similar to this on the exam. We want to predict the energy barrier to rotation for 2,2-dimethylprotein, or 2,2-dimethylpropane. We're going to draw both the staggered and eclipsing interactions, and we're going to use the table to calculate the energy cost. So let's first look at 2,2-dimethylpropane. So here's propane. At the 2 position, we've got 2 methyls. So that's your 2,2-dimethylpropane. Now, the nice thing about this problem is we can look at this from any bond axis and we will get the same answer every time. So what I'm going to do is draw this in a way that allows us to basically see the Newman projection a little bit easier. I'm starting at this carbon. You see we have 1, 2, 3 methyls. And now here's the other carbon right here. And there are 3 hydrogens here. If this is confusing you, pause the video and try to draw this Newman projection for yourself. Draw out the bond line for 2,2-dimethylpropane, and then try to draw a Newman projection. Now, every Newman projection for this will work. You don't have to look down a particular bond axis. But we're going to just look down this bond axis here. and we're going to draw our first staggered conformation. Now with this problem, all three staggareds are going to be the same. Okay, so notice the Y is at the top. So look, this is our perspective. That's an eye, by the way. See, the Y is at the top. And in the front, you've got 1, 2, 3 methyls. We'll call it CH3 or just an ME for methyl. And if we look at the back carbon, there are 3 hydrogens. That first one, that right there. And then we have the 2 on the bottom. That's your hydrogen. So if you're looking at this from the left, your wedges are going to be on the right. So let's call that A and that B. This is A, and that's B. All right, so now that we've got our staggered conformation drawn, let's draw the eclipsed. And all we really have to do to get to an eclipse is we're just going to rotate 60 degrees. And I'm going to simply rotate the front carbon. I'm going to hold the back carbon the same. So watch what I do here. I want to draw my Newman projection, keeping the back locked into place. All right, now because I rotated it 60 degrees, and I want to draw an eclipsing interaction. Remember, these are slightly, we have to draw them slightly offset just because it's way more clear this way. CH3, CH3, CH3. So now I've got my staggered and eclipsed conformations. Just going to clean this up a little bit. Now I can use the table and try to answer this question. So what is the energy barrier to rotation? So that means what does it cost to go from my staggered to the eclipsed and then back to the staggered? So let's start with our staggered conformation. Are there any interactions here that are listed on the table 4.6? Well, we don't have any eclipsing interactions in our staggered, and there are no gauche interactions, right? There's no gauche. You can only have gauche if it's 2 non-hydrogen groups. If you have a hydrogen and anything else, it's not gauche. So gauche means 2 non-hydrogen groups that are 60 degrees apart in a staggered conformation. I'll say that again. Gauche means you have 2 non-hydrogen groups that are 60 degrees apart in a staggered conformation. So basically, we have let's consider this a 0 kilojoule energy cost because nothing in our staggered conformation costs any energy based on the table. Now let's look at our eclipsed conformation. We see that we have 1, 2, 3 eclipsing interactions. Let's try to define each of these and assign an energy cost. Our first eclipsing interaction at the top is a hydrogen and a methyl. So we come to our table and we see that the hydrogen methyl costs 6 kilojoules per mole. And we actually have 3 methyl hydrogens, so these are all 6 kilojoules per mole. So if we add them up, we have 6 plus 6 plus 6. The total energy cost is 18 kilojoules per mole. So the Eclipse interaction has an energy cost of 18 kilojoules per mole. The staggered conformation has an energy cost of 0 kilojoules per mole. Therefore, the energy barrier to rotation is 18 kilojoules per mole. In this problem, we want to identify the highest and lowest energy conformation for the molecule, unlike the last problem where we just wanted to find the energy barrier to rotation between a very simple molecule by looking at the staggered and the eclipsed. So in this problem, we're going to take a look down the following bond axis because these two carbons have the most substituents. You'll always be told what bond axis to look down, but with this problem, I'm picking these two in particular because if I want to get the highest conformation, this is going to give me the most interactions. So, as we did before, we're going to make every Newman projection problem the same by creating our template. All right, so here are the two dotted carbons. That's an ethyl up top. We have a methyl. It's your wedge. We have hydrogen. Down here, this is an ethyl. And I have two hydrogens. And we're going to look down this bond axis here. So I'm going to draw all three staggered conformations, and I'm going to draw all three eclipsing conformations. So let's start with our first staggered. I'm drawing it as indicated by our perspective arrow. Drawing exactly what I see here. All right, so what we're going to do now is we're going to keep the back carbon the same. We're only going to rotate the front, so I'm keeping the back exactly as is. I'm going to rotate the front 120 degrees. So basically, I have to draw the next staggered, which puts my ethyl down here, methyl there, my hydrogen up top. I'm going to do the same thing for the final staggered. Rotate it another 120 degrees, keeping the back carbon the same. And again, it doesn't matter which one you keep, which one you lock in place and which one you rotate. It's all going to give you the same answer. So my final staggered conformation will put my methyl at the top and my ethyl here on the left. So as you can see, I'm rotating around to this front carbon, rotating around to the right each time, 120 degrees. So let's add up all of the interactions here, the staggers. So we're going to use the table on the left. And again, I'll always give you these values. Now, an ethyl hydrogen, there's no cost. Hydrogen, hydrogen, no cost. So that's 0, 0. But what we do have is a Gauss interaction, an ethyl-methyl Gauss. So let's find it on our table. Ethyl-methyl Gauss. This is worth 4.1. And again, the ethyl hydrogen doesn't cost anything. So the total here is 4.1 kilojoules per mole. Let's do the next one. Hydrogen costs nothing. Hydrogen methyl costs nothing. All right, 0. But we do have two Gauss interactions. I've got a methyl-ethyl Gauss. Remember, Gauss is two non-hydrogen groups that are 60 degrees apart. So my ethyl-methyl Gauss is 4.1, and the ethyl-ethyl Gauss is 4.5, which gives me a total for this conformation of 8.6. Is it 4. Ethyl Gauss 4.5. 8.6 kilojoules per mole. All right, our final staggered conformation: a methyl hydrogen 0, hydrogen ethyl 0, methyl hydrogen 0, hydrogen 0, ethyl hydrogen 0. But I do have one Gauss staggered interaction, the ethyl-ethyl Gauss, and that's worth 4.5. So my total is 4.5 kilojoules per mole. Now you know that your staggered conformations are going to generally be the lower energy conformations, but if we're looking for the lowest, that would have to be the first one we did. All right, so we determined our lowest energy conformation. Now to do the highest. To do the highest, we're going to have to look at all three eclipsed interactions. And we can start by drawing our first Newman projection, just like we did before. Keep the hydrogens. Clear this up a little bit. That's an ethyl. There's a hydrogen. Okay, now let's look at our first staggered. All I'm going to do is rotate that 60 degrees, and I see that my ethyl goes there, my hydrogen goes here, I have a methyl. All right, let's do the next one. We're going to keep the back the same. And I'm just going to rotate 60 degrees. And I end up with my next eclipsing interaction. And if I do it again, methyl, hydrogen, and my ethyl. So once I have all three eclipsing interactions drawn out, I can use the table to add up the energy cost. And my first hydrogen is going to be 4 kilojoules per mole. My ethyl hydrogen is going to be 7. And my ethyl methyl is going to be worth 12. So the total for this first one is 23 kilojoules per mole. And let's look at the second one, my methyl hydrogen. That's worth 6. Hydrogen, hydrogen, 4. Ethyl, ethyl is worth 13. See, their groups are larger. So my total for the second one is also 23 kilojoules per mole. And for my final eclipsed conformation, the ethyl hydrogen is worth 7. The methyl hydrogen is 6. Ethyl hydrogen 7, which gives me a total energy cost of 20 kilojoules per mole. So, to answer our question, we already determined our lowest energy conformation. That was the first Newman that we drew. It's a staggered. And our highest energy conformation, which has to be one of the eclipsed, well, it looks like both of these were 23. So these are equal in energy, and they're both the two highest energy conformations. So this approach, again, is a little different than the one that you saw in the notes, which was more qualitative. I think this one might be a little bit easier to understand because you're just using the tables and values that it will be given. All right, we're moving on to cycloalkanes. A cycloalkane is just a cyclic hydrocarbon. All of the carbon atoms will be sp3 hybridized with bond angles of 109.5 ideally. But we're going to see that they're not all 109.5. So if our cycloalkanes were flat, let's look at the bond angles that we would predict. So if they were flat, you'd see cyclopropane would be 60, cyclobutane 90, cyclopentane 108, cyclohexane 120, cycloheptane 129, and cyclooctane 135. But it turns out molecules are not flat. They're actually three-dimensional, and their bond angles are not the same as they were when we drill them flat in 2 dimensions. So how can we get some information about the stability and relative bond angles that they really adopt? Well, we can look at combustion analysis. So the heat of combustion, if you notice, cyclopropane is relatively high, and then it gets lower and lower and lower. Cyclohexane is the lowest, and then the heat of combustion per CH2 group increases. So what this tells us is that because cyclohexane has the lowest heat of combustion, that in 3D, this cyclohexane must adopt bond angles that are closest to the ideal 109.5. And it turns out that in 3 dimensions, cyclohexane does indeed have bond angles of 109.5. This is your optimum geometry around each of the sp3 hybridized carbons. So, moving along, let's look at some different cycloalkanes. Cyclopropane is the most highly strained and highly reactive. We saw it had one of the highest heat of combustions. The reason for that is because the bond angles here are about 60 degrees, and they cause a tremendous amount of electron pair repulsion. Additionally, the overlap of your hybridized bonds is not very good, so there's a lot of strain imparted on this molecule. Cyclobutane, also a very highly strained, very highly reactive molecule, in 3D has bond angles of 88 degrees. There's a lot of torsional strain here. And we can see that if you were to draw a Newman projection, nothing is really fully eclipsed or staggered. Cyclopentane is a little bit more stable, but slightly more stable than cyclopropane or cyclobutane. However, it's not quite as stable as cyclohexane, as we saw with the combustion analysis data. These angles, however, are pretty close to the 109.5 angle. So all that you need to know is that cyclohexane is the most stable. The rest are less stable. The smaller the bond angle, the more unstable it will be. Smaller the bond angle, the less stable it will be. You don't have to memorize anything from this slide, really. Our main focus is going to be on cyclohexane. So cyclohexane is considered to have zero ring strain. That's because there's no angle strain, because all of the bond angles are 109.5, and there's no torsional strain because all of the CH bonds are in the staggered position. So, although I'm not going to ask you to draw Newman projections for a cyclohexane ring, it is instructive to show that we have no torsional strain because if you look, everything's in the staggered position. And there's no energy cost for two hydrogens that are 60 degrees apart, and there's no energy cost for a hydrogen and a CH2 group that's 60 degrees apart. So we have no torsional strain because everything is in the staggered position. So the cyclohexane ring is the most stable, and the most stable conformation that it adopts is called the chair. So there are other conformations that exist, but they're slightly less stable. Our chair conformations are the lowest energy. The highest energy conformations are the half chair, and then we have twist boats and a boat. I really just want you to focus on the chair conformations. Chair is the most stable cyclohexane. And when I say most stable, I mean lowest potential energy. As far as the other conformations are concerned, just know that they exist. They're a thing. I'm not going to ask you to draw them or memorize their names. But they exist. There are higher conformations, higher energy conformations for cyclohexane. All right, you will have to be able to draw chair conformations. So it's really important that we can draw these properly. This requires practice. So there's a couple methods that I'm going to go over. The first is the books method, and then I'm going to show you sort of my way of doing it, my way of drawing the chairs. So the book outlines a method where we draw 3 sets of parallel lines. So if we look here, you draw 3 sets of parallel lines. You want to start with your first set, and then we can draw our second set. And then we can draw our third set. All right, this takes a little practice, and it's kind of hard to do on this touch screen. However, once you get that down, then we have to put the substituents in the right place. So there are axial and equatorial groups. Axial and equatorial substituents. 6 of the atoms attached to the chair are axial, and they are in alternating positions. So you could start by the tip that's pointing down and your first axial is down, and then you go to the next carbon, your axial will be pointing up, and you just alternate. Down, up, down, up. You just have to know where to start. What you don't want to do is look at the tip pointing down and draw your first axial substituent up. So just remember, wherever the tip going down is, that's your first axial substituent going down. Alternate carbons up, down, and you're good. Now the next set of substituents are equatorial. So equatorial substituents are positioned at angles are parallel to the set of parallel lines that you've made up. So you can start really wherever you know you had a axial there. So let's put our axials in. So if one of the substituents was axial, the other has to be equatorial. So we can just go around and draw our equatorial substituents. All right. So that's one method of doing this. This just takes practice. I'd like you to show I'd like to show you an alternate way of drawing these chairs. This is sort of how I go about it. Once you understand your basic framework, if you can get yourself to drawing the basic framework here, then the rest is really just about putting the substituents on the correct atom. So I always start with the tip pointing down with this carbon, and I remember that each carbon has one axial and one substituent. So we can start by putting our first equatorial, and I know that on the bottom face of the ring there's going to be an axial. And then I just alternate, I just flip-flop. So on the top face of the ring, so I think of the ring as having two faces, a top face and a bottom face. On the top face of the ring, I had an equatorial. On the bottom face of the ring, I had an axial. On the next carbon, it's going to be flip-flop. On the top face of the ring, I have an axial, and on the bottom face, I have an equatorial. Let's go to the next carbon. On the top face, it has to switch now. It should be equatorial. The bottom face is axial. The top face is axial. Bottom face equatorial. The next carbon, the top face of the ring is equatorial, and the bottom face of the ring is going to be axial. On the last carbon, we have axial and equatorial. Now, you'll probably have one method that you prefer over the others. However, stop the video, try this on your own, and then when you come back, I'm going to show you how to do the ring flip. So the ring flip, it's not a flip like a pancake, all right? It's actually a rotation about certain bonds. And we're going to get to this in the next slide. However, I want to draw it here first. When we do a ring flip, we're drawing our chair in a flipped conformation. So this is your flip. Now, this carbon, the dotted carbon, is right here. So just for labeling sake, let's call that 1, 2, 3, 4, 5, and 6. Here's carbon 1, 2, 3, 4, 5, and 6. And all we have to do is put our substituents in. I always start with the tip that's pointing down. We know that on the tip that's pointing down, your axial always has to go down, and your equatorial is going out. Now we just alternate. And remember, I think about this in terms of the top and bottom face of the ring. So on the first carbon, my equatorial was on the top, the axial was on the bottom. On carbon 2, I want to draw my axial on the top and my equatorial on the bottom. On the next carbon, draw your equatorial on the top, axial on the bottom. And we just keep going around the ring. So that's how you would draw your cyclohexane chair ring flip. So this also requires some practice. So you can pause the video and try to draw the flip version if you want. And once you get it, come back and we'll go to the next slide. All right, so I kind of just showed you how to do that ring flip. And that's important because we're going to actually put some substituents on these cyclohexane rings. So there are two possible chair conformations, one with a substituent in the axial and one in the equatorial. So this is just that flip that I just drew. These are the same carbons. Notice the substituent is axial, and here the substituent is equatorial. Right. And again, flipping the chair is not like flipping a pancake. It's a result of carbon-carbon single bonds rotating. So you actually get a bond rotation that causes this flip and your substituents to go from equatorial to axial. So you might have to just stare at this and try to think about how this is working and really see this. I recommend drawing or actually building the model for this. If we were in class right now, I would have my big model kit and I would show you how this flip works. Hopefully you have a model kit and you can do this on your own. All right, so in a typical problem, we want to be able to draw both the chair conformations for bromocyclohexane. So let's look, what is bromocyclohexane? We have cyclohexane with a bromine. Now, it doesn't matter if you put it with a wedge or a dash at this point. All right, so really is irrelevant because you could flip that like a pancake and it's the same molecule. These are not isomers in any way. It's the same exact molecule. So we're going to draw both chair conformations. Let's start with the first one that we learned. Okay, step 1, draw the chair. Step 2, draw in all of your substituents. Okay, now we have to put the bromine in. All right, so pick a carbon. It doesn't matter. Let's just say, let's start with the carbon with the bromine. And now let's just pick any one. We'll say that this is our carbon with the bromine. And because I have my bromine here written as a wedge, that indicates that it's on the top face of the ring. So let's put it here. I'm putting it in the axial position because I have a wedge drawn. Now, it's not that a wedge means axial. The wedge simply tells me that the bromine is projecting out of the plane of the board and is on the top face of the ring. So I'm choosing the top face to put my bromine. Now to draw my ring flip, draw the flipped version. Let's put in our substituents. Okay, and remember, let's look at our carbon that has the bromine. That's carbon 1, 2, 3, 4, 5, 6. This is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. So where do I put the bromine? Because the bromine is on the top face of the ring versus the bottom face, see in the bottom face I have a hydrogen here. We're going to keep our bromine in carbon 1 on the top face. And the hydrogen is on the bottom. So in our first version, bromine was axial, and in our flip, it was equatorial. The rest is easy. You can just fill in your hydrogens and the rest of your substituents here. And we're done. Now, for monosubstituted cyclohexane chair conformations, we have to be able to assess the stability of each flipped version. So this is really simple. If your substituent is axial, that's less stable, meaning it's higher in energy. If your substituent is in the equatorial position, it's lower in energy, which means it's more stable. And the data shows us that we can actually measure how much time a chair will spend in a particular conformation. And 95% of the time, our chair will exist in a monosubstituted cyclohexane will spend most of its time in the chair position with the substituent in the equatorial position, because equatorial is more stable. If both chairs were equally stable, we'd have a 50-50 mixture, but we don't. We see that we have a 95-5 mixture. So equatorial is more stable than the substituent in the axial position. So you may be wondering why, and the answer to that can be explained through something called 1,3-diaxial strain. 1,3-diaxial strain is simply due to steric strain or steric hindrance. Bulky groups have electron density that repel each other. So when your groups are in the, so we have 1, 2, 3 position, there's 2, and then there's the 3 position. The 1,3 interaction is essentially a CH2 group in a Gauss position, in a Gauss staggered position with a methyl group. So that's for a substituted cyclohexane. Remember, Gauss interactions cost energy. So a methyl-methyl Gauss is not the same interaction as a methyl hydrogen Gauss. This is 0, but a methyl-methyl Gauss has an energy cost. So The reason that equatorial positioned substituents are more stable because of 1,3 diaxial strain, which essentially means that you've got a Gaussian interaction occurring for your axial substituent. Let's take a look at a di-substituted cyclohexane. When we draw our conformations, you have to consider the 3D orientation. So if you're given a Lewis structure and we're asked which one is more or less stable, which conformation is most stable, which conformation is least stable, we're going to have to draw both ring flip versions. So if you're given a Lewis structure like this, you want to draw both ring flips, put your substituents in, and we can assess the stability. So notice how the chlorine is on the top face of the ring and the methyl is on the bottom face of the ring. So we can be consistent here with my chlorine on the top face and the methyl on the bottom face. And remember, you've got hydrogens here. So they're opposite of each other. Chlorine is still on the top face and your methyl is on the bottom face. Okay, so this is a typical problem for a di-substituted cyclohexane. We're going to draw both chairs and we're going to determine which is more stable. So remember, your ethyl is in the top face and the methyl is the dash that's going to be in the bottom. So let's draw the first chair. We're going to put our substituents in. Let's call the ethyl carbon 1, the ethyl carbon 1, 2, 3, 4, 5, 6. We can start here with carbon 1. It's just a matter of preference. The ethyl is a wedge, so that means it's on the top face of the ring. All right, and I've got a hydrogen there too, so I can put my hydrogen in. Carbon 2. I've got 2 hydrogens. At carbon 3, I have a hydrogen and a methyl. Hydrogen's in the top face, methyl is in the bottom. And carbons 4, 5, and 6 have substituents that are all hydrogen. All right, so let's look at what we have here. An ethyl, that's axial, and a methyl, that's equatorial. Let's draw the next flipped chair version. Okay, we can put our substituents in. And remember, if this is carbon 1, carbon 1 is right here. 1, 2, 3, 4, 5, and 6. My ethyl group is on carbon 1, and it's on the top face of the ring. So carbon 1, top face of the ring. Hydrogens on the bottom. On carbon 2, we have 2 hydrogens. Carbon 3, with my methyl, there's carbon 3. We see that the hydrogen's on the top face of the ring, and the methyl is on the bottom face. And the rest of the carbons just have hydrogen substituents. Okay, so in this chair version, I've got an ethyl group in the equatorial position, and a methyl group in the axial. So let's compare the stabilities. Remember, equatorial is more stable. So I've got, in my first chair, I've got a methyl that's equatorial. I've got an ethyl that's axial. And in my second flipped chair, I have my methyl in the axial, my ethyl in the equatorial. So we have to look at both of our situations and figure out which chair version is more stable. Well, because equatorial is more stable, I probably want to put the largest group, right, in the equatorial position. And that's this chair version here with my ethyl being larger than methyl in the equatorial position. So this is your most stable chair. Let me summarize what I've done here. From my Lewis structure, I draw both chair versions, put the substituents in the correct place. I assigned equatorial and axial for the substituents, methyl and ethyl, on each. I used the concept of equatorial being more stable, and I looked for the largest substituent in the equatorial position. And that's the second chair version that I drew. All right, the last section deals with cis and trans stereoisomers. A stereoisomer, which really is the focus of Chapter 5, is simply an isomer that has the same formula, same connectivity, but a different spatial arrangement. So stereoisomer means same formula, same connectivity, but a different spatial arrangement of your atoms. So we've got two forms of cyclohexane, a disubstituted cyclohexane. That's the cis and the trans. Cis is when your substituents are on the same face of the ring. Trans is when your substituents are on opposite sides. If I wanted to draw a Lewis structure for this, I could put in my substituents just like this. Cis means they're on the same face, so they should both be a wedge or both be a dash. You could also have drawn it like this. Both cis, both the same molecule. And for the trans, if we wanted to draw a Lewis structure, we'd have to have our substituents on opposite faces of the ring. One being a wedge and one being a dash. All right, so that's it for Chapter 4. We're going to move on to Chapter 5 in the next lesson. So please remember to try working through the homework problems that are listed on Blackboard and check your answers.